All right, so let's get started for the class. Okay, so on Monday, we stop at example 3.8. So today we are going to continue our discussions on stator bolts. Okay, so I noticed there are some students missing on Monday, so you better pick up what you missed on Monday. We cover example 3.7 and 3.8 in the textbook, so we don't need to spend time to repeat here just for you. Okay, and also one thing I would like to make sure, can you guys access the Pitchboard to download the homework? I think I uploaded last week, Wednesday already, but I heard the Pitchboard has some problem this Monday, so I'm just wondering, can you guys check?
I checked earlier today and it was working again, for me at least.
So it's working, everything's fine?
Yes.
Yeah, it was working, yeah.
Thank you, Andy. How about Erica? Can you download? I think you mentioned on Monday, right?
Yes, I was able to download it, no problem.
Okay, great. So it's good to know. Thank you. All right. So let's continue our discussions about the Steger fastener. So on Monday, we talked about the plate and the angle with the Steger fastener. So today we'll continue with different shapes. For example, the channel and the S or W shape. So if you have a Steger fastener on the channel or the W shape, then if the bolt on this flange to the edge is G, and this bolt to the edge is G1, and the thickness of the channel of this channel is TW thickness. So now to calculate the net area, we have to do the scale like we did as an angle. We need to unfold meaning we need to unfold, make it like a plate. So we need to unfold this and make it like a plate. So if we unfold, it will look like this on the right hand side, okay? So you unfold and it becomes this. So your gauge distance between these two bolts will be G plus G1 minus TW. So please remember this skills. As for W shape, same thing, but this is a little bit tricky here. What you have to do is you unfold with respect to center line. So you unfold and make it like a plate to the right hand side like this. Okay, so the gauge distance between this bolt and this bolt will equal to half G plus G1 minus TW divided by 2. Okay, so please remember these skills. Any questions? This is just a different way to define the gauge distance between the bolt on the flange and the bolt on the web. Same thing, this is on the flange and this is on the web. So this bolt is this bolt, and this bolt is this bolt. Same thing, this one is this one. And the red color here is this guy. Okay? Any questions or discussion about this slides?
No, sir.
Okay. So now with that being said, let's move on to example 3.9. So the problem wants you to find the available strength of this S shape in figure 320 in here. The hole will be 3/4 inch diameter bolt and use A36 steel. So this is a cross-sectional view and this is a side view. Okay, so this is bolt B and this is bolt C. And this is the bolt on the flange. This is the bolt on the flange. So if you look at the side, for this bolt, you got 2 bolts here, but actually you got 4, because on the other side of this flange, you got another 2 in here. This is only side view. So in this case, on the flange, you got actually 4 bolts. Okay? On the web, you have 2 bolts. One is B, one is C. Same thing for bottom flange. You got 4 bolts. Each flange, half of the flange, you got 2. So you got 2 of them. So total is 4. Okay? So this is the problem statements regarding the bolt layouts. Now, any questions regarding the problem statements?
No, sir.
Okay. Now, to find out the available strength, which is the based on LRD and ST, we need to figure out the strength based on yielding and the strength based on fracture. Okay, and then we pick the minimum as the governing strength. Okay, so to calculate fracture, we need to calculate the net area first. So the net area for stagger fastener, as we discussed on Monday, there are few possible failure paths for stagger fastener. So if you look at this side view, can you guys tell me what would be the possible valid failure path?
A, B, C, D, or AD.
A, B, C, D, great. And another one is AD. All right, anything else?
No.
No? Okay. So, we need to calculate each path, failure path, the A net for each path. So, because like I told you on Monday, because this shape is non-uniform thickness, so to compute net area, you have to use this equation. A net is equal to AG minus summation T times D or D prime. So we will start with the effective hole diameter, which is 3/4 plus 1/8 is 7/8. So now from line AD is non-stagger fastener for the failure path. All the bolts is on this line is non-stagger. So for the line AD is very straightforward. You just need to use AG minus how many bolts? In this case, anyone?
4 total.
For AD, it would just be 2, correct?
For A, how many?
For AD, it would just be 2.
A, D, only 2?
4.
You're looking at only one side. Don't forget, This is actually 2 sides. So how many?
4.
So 4.
4. So it's 4. Okay? And then times the effective hole diameter and times the thickness. Now the thickness is which thickness? Is it thickness on the flange or thickness on the web?
On the flange.
On the flange. So you make a note. This is the thickness of the flange. And then with that being said, you calculate 12.52 inch squared for A net. Any questions or discussions?
No, sir.
So to come up with this value, you need to check the manual, part 1, and looking for S15 by 50. So you guys can go ahead and do it. Maybe spend like 1 minute or so to get this number. If you can get it, let me know.
Where did the 0.622 come from?
It's the thickness of the flange.
Oh, we just find that through the manual.
It's also in the manual.
Okay.
Thank you, Lin, for the input. Now, let's look at the other failure path. We're talking about AB, CD. Now for AB, CD, remember the gauge distance between A and B, you need to follow the formula. I just give it to you. For the gauge distance G, you need to use this formula. It will be half G plus G1 minus TW over 2. And therefore you got this number. So the G between A and B is 4.225 based on the previous slides that we just covered. Same thing applies between C and D. So these are the same because they are symmetric. Any questions? Any questions?
No, sir.
Okay. Now, so with them being defined, let's move on to calculate the net area associated with this failure path, AB, CD. So now the gross area 14.7 and minus summation T times D or DW. So you got to identify the bolts on the failure path is stagger or non-stagger. All right, so let's starting from point A and move on to B, C, and D. So now, in this case, starting from bolts located at point A, can you tell me for these 2 bolts, are they stagger or non-stagger? You need
Non-staggered.
D or D prime.
Non-staggered.
Just
So you
read
use D or D prime.
D.
D, great. So you got 2 of them. And the effective hole diameter is 7/8. And this thickness is what? The flange or the web?
The flange.
The flange. All right? So this will take care of the bolts at A. Now let's move on to bolt B. Can you tell me bolt B is stagger or non-stagger?
Staggered.
Stagger. So you need to use D or D prime.
D prime.
D
D
prime.
prime. All right. So D prime, we need to use D prime. So this is D minus S squared divided by 4G. So we just calculate the G between A and B, which is 4.225. And this thickness is the thickness of the flange or the web.
Web.
Well,
The web, that's correct. And how many bolts we have at B?
just one.
1.
Just one. So nothing here, just times 1. So that's why you use point minus 0.55 and break it. This whole term is what we call D prime.
Did we
So far,
calculate?
okay?
Sorry, did we calculate for 4.225? Or is that in the manual?
We just calculated, right?
Okay.
Here. We just calculated.
Okay, I see. Thank you.
Uh-huh. So now the next path will be from B to C. So can you tell me C is a stagger or non-stagger?
Non-staggered.
It's non-stagger, right? So it's non-stagger. So you have to use D or D prime.
D.
D. So that's great. So let's move on to here. You got to use D instead of D prime. Then this thickness, same thing is on the web. So 0.55 times 7/8. All right, now, how about from C to D? Is D stagger or non-stagger?
Staggered.
Staggered.
Stagger. So you have to use D or D prime.
D prime.
D prime, that's correct. So now you have to use D prime here. Which is effective hole diameter D minus S squared over 4G. And then this is the thickness of the flange. How many bolts in this case?
2.
So you need to times 2. Any questions?
No, sir.
Any questions? No?
Professor,
Yeah, go ahead.
on the flange, are there 2 bolts on top and bottom or 4 in total?
Yes, because in this case, we take care of that in here.
Oh, okay, thank you.
Mhm.
Professor, can you show the previous slide one more time, please? The one.
This
before
one?
No, the one.
Oh, this one?
Yes.
No.
Thank you.
Okay. right, so with that being said, see. So, which one govern? Is AD or ABCD govern?
ABCD.
ABCD.
ABCD govern. So, the minimum control one is 11.73. And as you guys know, AE, effective area, is equal to U times AN, right? But in this case, because all the elements of the cross-section are connected, so there's no shear leg effect. So U is equal to 1. So AE is equal to A net is equal to 11.73 inches squared. So for the net section, the nominal strength for fracture is FU times AE. So it's 58 times AE is 680 kips for nominal strength based on fractures. Based on yielding is FYAG. It's about 529.2 kips. All right, so this is the nominal strength based on fracture, and this is the nominal strength based on yielding.
Was that in the problem statement, sir, or is that in the book? The strength for fracture and yielding.
Which one?
FU, FY.
F1, FY, and FU?
Yeah, was that given in the problem statement?
Yeah, it's A36 steel.
Thank you.
Mm-hmm. So like I said before, if you read A36 steel, you need to go to manual table and to figure out the number for FY and FU. So this is what we talked about that before. Any other questions?
No, sir.
No? Okay. So, the design strength based on fracture will be Vt times Pn. 0.75 times 680 is about 510 kips, 510 kips. Design strength based on yielding is 0.9 times Pn is 476. So in this case, the minimum control. So in this case, is yielding will happen first. So the design strength is 476 kips for this tension member in the connections. So the yielding will happen first before the fracture. So this is what we talk about, the design strength based on LRD. Any question up to now?
No, sir.
Okay.
The Vt and the design strength, is that also in the book, or is that just part of the equation?
It's part of the equation is in the specification.
Right, for LRFD and ASD.
Uh-huh.
Okay.
Mm-hmm.
Stop it. Now, stop it. Stand up straight, Elizabeth. Stand up straight. I can't believe you. No, I can't answer.
Any questions?
No, sir.
Okay. And then, based on ASD, if we use allowable stress approach, the allowable stress based on fracture is 0.5 FU. So allowable tension stress based on fracture is 29 KSI. So the corresponding allowable strength would be FT times AE is 29 KSI and times AE, which is the one we just calculated, is 340 kips. The allowable stress based on yielding is 0.6 FY, is 21.6 KSI. So the corresponding allowable strength is FT times AG is 318 kips.
Let's go. Let's go.
So the yielding, again, will control based on AST. So allowable strength is 318 kips if you use AST
Let's go.
approach.
Let's go or no? No? No work? No?
Any questions
Yes, okay.
for this example?
Let's go.
Sir.
Okay.
So for allowable strength versus design strength, is that just determined based off of LRFD and ASD? Or-
Yeah. In LRFD, we typically call design strength. In ASD, we typically call allowable strength.
But it's basically the same thing. It's just the way that you got there.
The nominal strength is the same, but the reduction factor phi and the safety factor is different. Like I said in chapter 1 and chapter 2, the design philosophy is different. But the nominal strength is the same. Doesn't matter you are using ASD or RFD.
Come on, man, let's go.
It's the way you calculate so-called design allowable. It's different.
Yes,
Later.
sit on your leash, bro. Hey, sit.
So based on those two strengths, do we choose the minimum?
Which two strengths?
The design strength of the allowable strength?
There are totally two different design concepts. So you cannot say you're going to pick minimum out of the two. It's not like that. Like I say in chapter 2, if you stick with the RFD, you have to use the RFD to design your project. You cannot mix both. So it's not like 476 and 318, you pick the minimum. It's not like that. It's different design philosophy, okay? Because like I said, the demand is different. For RFD, your demand is factor loads. ASD, your demand is service loads. So they are totally different design philosophy. So LRFD is one solution, and ASD is another solution. Review chapter 2 and study the book. You understand that we covered in chapter 1 and 2 before. Review the class and the book. Any other questions?
For the ASD approach, we can just use the nominal strength
Divided by factor safety.
of safety, right?
You can do that too.
Thank you.
That we call allowable strength. Remember? We call allowable strength approach, such that you got your P allowable is equal to P net divided by factor of safety, which is omega. So Nada, is that your questions?
Yes.
So is it clear now?
Yeah, thank you.
I remember one student asked on Monday before. I think it's Gary, right?
Yeah.
So yeah, so it's the same thing. You can use allowable stress or allowable strength for SD. You will reach the same answer. Any other questions or discussions?
So just practical application, this would be like if you're looking for a tension member that's going to hold 500 kips, then you would test it like this and then see that this geometry wouldn't pass.
For practical application, meaning this is your capacity, 476. So meaning your design load, your loading should be smaller or equal to this amount. So meaning your factor load combination of your factor load should be less or equal to 476 kips for this member. So this is the maximum load this member can take compared with the combination factor load.
Perfect. Thank you.
Same thing, to answer your questions. For SD, this should be bigger or equal to your combination service load. Okay? So 476 is the capacity based on the tension member, LRFD. 318 is the capacity based on ASD. Okay? Any other comments, discussions?
Yes, sir.
Okay. So with that being said, we finish the stagger bolts sections. So it's quite a journey, and but finally we finished that one with different shape of tension member. If you encounter any stagger bolts, and for any shape, I think you guys should not have any problem for now. So that would be that for the stagger bolts. Now we are going to move on to the next sections. Which we call block shear rupture. So this is section 3.8, block shear rupture. So the block shear in some way is similar to tension rupture. In the main part of the member, tear away from the connections. But the difference is that there's a now combination of tension and shear on the failure path. So like tension rupture, there frequently is more than one failure path. So in this figure 16, it shows a block shear path, failure path. For WT sections. So if this is a WT sections, as you can see, the bolts is two lines of bolts, one here, another bolt line is in here, and this is a side view of the WT. And if this member is under tension, as you can see that there are three possible failure paths due to block shear. So it's basically will tear out pieces of the member. So as you can see that failure path 1, the piece of this guy is being torn out, tear apart like this. Another path will be like this. The whole piece got torn out. And another possible path will be like this. The whole piece is torn out like that. So this is what we call block shear. How come we call block shear? So by the way it look, is the block of the member has been pulled out and ruptured. And as you can see that under tension load, there are a combination of stresses happening. There are shear stresses and the tensile stresses on the block. So if you zoom in to this one, you will see that the shear stresses happening on the line parallel to the loading directions. Okay, so this is shear stresses. And on the other hand, on the line perpendicular to the loading, you will see the normal tensile stresses happening on this line. Okay, so the block shear is actually the combination of shear stresses as well as the tensile stresses. Any questions or comments and discussions?
No, sir.
Okay. So, block shear rupture. For a certain connection configuration, a segment or block of material at the end of member can tear out. So, for example, the connection of single angle tension member shown in figure 17 is susceptible to this phenomenon called block shear. So for the case illustrated, the shaded block will tend to fail by shear along the longitudinal section AB and by tension along section BC. Okay? So this is another example for the block shear failure. Any questions or comments?
No, sir.
Okay. So now, for a certain arrangement of bolts, the block shear can also occur in cassette plate, not only in the tension member, but also in cassette plate. So for example, figure 18 show a plate. So if this is a plate as a tension member connected to a cassette plate below. In these connections, the block shear could occur in both cassette plate and tension member. So please be careful. For this kind of connections, the block shear could happen either in tension member and also in cassette plate. So for this case, you need to calculate the block shear strength limit states for cassette plate as well as the tension member. And you need to pick the minimum as the governing block shear strength limit states, because it might fail in cassette plates, it might fail in tension member for block shear. You never know which one will happen first. So you have to do calculation for cassette plates, block shear, and tension member block shear. Strength limit states. And then you pick the minimum out of the two as the governing strength for block shear failure. Okay, so remember what I just mentioned here. For cassette plates, in this picture, tension failure would happen along this DEFG. So DF will have the tension failure. And for DE and FG will have the shear failure. Okay, so this is what we call longitudinal service, and this is what we talk about transverse service. So this is on the cassette plate. And same thing apply for the tension member, then it will be happening between this block. All right, so the tension will happening on IK, and shear will happening in HI and JK. Any questions?
No, sir.
All right. So for block shear definitions in the equation for the shear strength, a block shear strength, let me state you need to go to chapter J, design of connections, section J 4.3, and in 13 sections, 13 edition of the manual will be page 16.1-112. So you can go there and to see the strength definitions. So here, we are going to go over the equations. So the model used in the AIC specification assume, okay, the failure occurred by rupture on shear area and the rupture on tension together. Both surfaces contribute to the total strength, and the resistance to the block shear will be the summation of the strength of the two surfaces.
Yes, hi. I wanted to speak with Mrs.
Both the shear and the tension. So it's a combination of
Absolutely.
those strengths.
Jocelyn Del Angel, if she can just return my phone call.
The shear rupture stresses is taken as 60% of the tensile ultimate stress. So the nominal strength in shear is 0.6 Fu times AMV. So this is the ultimate tensile strength. And we take 60% of that as our shear, nominal shear strength. Okay, so this Fu times ANV is the tensile ultimate strength times net shear area. So AMV is the net area along shear surfaces or surfaces. Is we call ANV. So the ANV is here. Let me go back to define that for you. We'll come back. So here, the area along this line is what we call AMV. It's the net shear area. And the area between J and K
Jocelyn,
is what we call ANT. Is the net tension area.
It's 323-479-7759.
Okay?
I also left
So-
a message.
Just remember the definitions. So same thing apply here.
Sorry,
And A net
that's correct.
on cassette plate
Diana
is in
Gordon.
here.
Correct.
So
Evelyn
AMV
Medina.
also in here.
Evelyn
Okay.
Medina.
Any other questions?
No, sir.
Okay, and then let's go back to here. So here we assume the nominal shear strength
Maria
is 0.6 FU AMV. And the nominal strength in tension, of course, no reduction. It's just FU times ANT. So ANT is the net area along the tension surface.
Correct. I left a message about 2 weeks ago.
So this is AMV
Correct.
and this is ANT. Do not confuse.
Thank you very much, man. You have a wonderful day. Okay.
So this will give you the nominal strength of block shear is a combination. Combination of what? Shear plus tension. Strength. So the first term here is the shear.
¿Qué te dijo?
Nominal shear strength. The first term. Second term will be the nominal tensile strength on ANT. And this is the nominal shear strength on AMV. So first term, this guy. Second term is this guy. So combination of the two will give you the nominal strength of so-called block shear.
Yes, hi. Am I please speak with Princess? Hello, ma'am. My name is
Any
Jocelyn.
discussion or questions?
Jocelyn Del Angel, and I'm calling in regards to
No, sure.
Marie Reese.
Okay.
Hello, ma'am. I was just calling because I think Marie has given you a little bit of background in regards to who I am. And I just wanted to check in and see how things were going in regards to her complying with everything.
Any other questions or discussions? No? All right. And then, however,
I think she's giving you permission, no?
the AIC specification uses the equation above for angle in cassette plates.
I see. I just wanted to help and make sure she was.
So the above equation
I know.
you just learned is applied for angle in cassette plate
Just wanted to check if things were
connections. For certain type of cold beam connections, the second term is reduced to account for non-uniform stresses, tensile stresses. So what do I mean by cold beam connections?
Okay, ma'am. Okay, thank you very much. You have a wonderful day.
So that will be in chapter 5 for the beam connections. I don't know if you guys seen this before in the field. If you got two beams connected, the W shape connected, you usually see this kind of cope beam connection. So this part has been coped in order to make the connections. So to account for the block shear might happen in here. Okay? So in that cases, the cope beam connections, the second term in the block shear equation will be reduced to account for non-uniform tensile stresses. So for those cases, You have a non-uniform stresses, you need to times 0.5 on the second term. So this is the notes I would like to mention to you. Okay, if your tensile stress is uniform, then this is equal to 1. No reduction on second term. And also, the specification also limits the 0.6 FUMV term to maximum value 0.6 FYAGV. So what is GV? Is the gross area along the shear surfaces. And 0.6 Fy is a shear yield stress. Okay? So with that being said, the final equation in chapter J of your manual to cover all the cases is 0.6 FUMV plus UBS FUNT. And the limit will be 0.6 FYAGV and plus UBS FUNT. And the UBS, this term, is equal to 1 when tensile stress is uniform. If you have an angle, cassette plates, and most of the cold beams. And 0.5 when tension stress is non-uniform. And when is the cases for non-uniform, you need to look at the commentary of the specification. For LRT, the resistance factor for block shear is 0.75. For ASD, the safety factor omega is 2. And this equation for block shear usually is expressed in terms of bolted connections. But the block shear can also occur in the welded connections as well. So if you have a welding, you need to also check block shear by welding. Same thing, there's a combination of shear and tension. It's just the way you calculate this is different. You calculate AMV and AGV as well as FU and FY on that term is different. Okay? Any questions or discussions?
No, sir.
So this will be the equations for the block shear. So, if you are using RFD versus ASD, the RFD is the demand by factor load combination should be less or equal to Vt times R nominal for block shear. So your phi, like I said, is 0.75 in this case. For ASD, your allowed demand from surface load combination should be less or equal to the nominal block shear strength divided by omega. Omega is factor of safety is equal to 2.
Based on that letter, Murray?
So this is what we call allowable strength.
Did you? Okay, let me hear it. Mándamela.
So you divide by omega to figure out your capacity. Capacity should be bigger or equal to your demand.
What? Okay.
Any questions or discussions?
No, sir.
All right, so if not, I think I will stop today's lecture at this point. And as usual, I will stay here to answer any question you guys have. But just remember that please start to work on your homework number 2.
What happened?
Since you already covered most of the problems already, we're towards to the end of lecture 3. So you should start, like I said, start to work on the problems in homework number 2 up to block shear. And next week we'll continue